my name is Alexis San Miguel, and I will be presenting the second law of thermodynamics. So the foundation of the second law of thermodynamics was developed in the 19th century by Rudolf Clausius and Lord Kelvin. These physicists conducted experiments and developed theses based on observations made for heat and energy in various systems. So for Kelvin's statement, it can be interpreted to state that no heat engine can be at 100% efficient, meaning it is impossible to convert all the heat and energy input into useful work without some energy loss as waste heat. Clausius' statement regarding the second law of thermo is one of the fundamental concepts used in heat transfer, stating that heat does not naturally flow from a colder body to a hotter body without the input of external energy. And a new term that's introduced is entropy, where the concept of entropy is central to the second law of thermo. Entropy is used to describe the amount of energy that is not available to do work. The second law predicts that in any energy transfer or transformation, the total entropy of an isolated system can increase over time, reaching a maximum efficiency. The second law distinguishes between reversible processes and irreversible processes, and the second law is able to determine whether a process is feasible through the concept of spontaneity. Spontaneity is simply the process change that is able to happen without the need for external intervention, such as additional work. Spontaneity occurs when entropy is greater than 0. Why is it needed? So the second law actually addresses some of the limitations that occur in the first law, such as the feasibility of a certain process and change of state, the direction of flow of heat, and applies conditions for equilibrium. So some of the equations are: the second law of thermodynamics is equal to delta S equals Q divided by T2 minus Q divided by T1, where equilibrium occurs when delta S is equal to 0. And you're able to find the maximum efficiency of a heat engine when delta S is greater than or equal to 0, and in this case you have Q2 and Q1, which are just different reservoirs. So it's delta S equals Q2 divided by T2 minus Q1 divided by T1, where Q2 is the smallest corresponding equilibrium condition. And you can rearrange this equation to say Q2 divided by Q1 equals T2 divided by T1. And thus you can find the maximum efficiency is equal to 1 minus Q2 divided by Q1, or 1 minus Q2 divided by T1. And then you also have the Gibbs free energy equation, which is delta G equals delta H minus T times delta S, which when the Gibbs free energy is in equilibrium, you can set enthalpy as a function of entropy, which is just delta H equals T times delta S. And since enthalpy is a function of internal energy, you can also state that delta U equals T times delta S minus delta P times V. And some applications of the second law include heat engines. The second law is fundamental in the operation of heat engines, such as internal combustion engines, from a high temperature source, and can be converted into useful work, as some work must be lost as waste heat. The law helps engineers design and improve the efficiency of engines. And then you have refrigeration and air conditioning. where the second law governs the operation of refrigeration and air conditioning systems. These systems move heat from low temperature space to a high temperature space, but require energy to establish this. The law helps in designing of efficient cooling systems. And finally, power plants. In power plants, whether they use fossil fuel, nuclear, or renewable energy, the second law applies in determining how efficient the heat generated can be converted into electricity. Power plants aim to minimize waste heat. And those are my sources.